Swayam Prabha. Digital India. Educated India.
Where we derived these expressions for parameters and the expectation step, the M step and the expectation step. And do please remember that expectation of indicator variable is a way of getting the expected count. Okay, expectation of indicator variable can be summed to get the expected count. Very useful point to remember in probability. So from that, we got the dictionary correspondences in this form purely from the parallel corpus. The corpus gives you these parameter values, the probabilities of alignment. The expectation step gives you the expected count of the alignment. Okay, what is the expected count of 3 mapping to Troya? Okay, now this was a very fundamental problem in machine translation, especially data-driven machine translation, and is of critical importance in all of data-driven MT, SMT, and MT everywhere. So do pay some attention to this derivation of alignment formulae. Okay, very rich in possibilities. Now, and here let me also tell you that this derivation is really very well worked out in my book. Okay, so I'm not trying to promote my book. I'm just saying that this is very well worked out in my book, and this kind of treatment I have not seen in papers and other books. So I think starting from 1 coin to 2 coin to multiple outcomes to the alignment problem, it's a nice way of developing the topic. Now we come to the technique which is used in today's in modern machine translation, which is recurrent neural network. We have just touched upon it. Today I'd like to do in some detail RNN and CNN, the 2 modern pillars of deep neural network, will be more extensively discussed and elaborated in the next semester's course on deep learning for natural language processing. So recurrent neural network, we know, is a single network moving over a sequence of entities. So the weight U, V, and W, where V is going to the output neurons, and X is the input neurons going into the network which has state S through the matrix U, and the network feeding itself through the weight matrix W. Okay, this gets unfolded in time. So this unfolding is very important for recurrent neural network. Now, recurrent neural networks have feedback connection, as is shown here also. This makes the network iterate and reach a stable configuration after some time. The question of stability is important for recurrent neural network. And there is a very celebrated network called Hopfill-Net, which we did not find time to discuss. This is really the foundation for recurrent networks. Now, Hopfill network is actually limited in computational power. You can show that the Hopfill network has to reach a stable configuration in order n square steps, where n is the number of neurons in the Hopfill net. And the Hopfill net minimizes what is called the energy. So minimization of the energy can be corresponded with minimizing some quantity. For example, the minimizing the tour length of a traveling salesman. Okay, so the Hopfill net has to reach the final state in order n square steps. So any problem which is beyond order n square in complexity is not tackleable by a Hopfill net. but Hopfield nicely laid down the theory of stability, made use of the energy expression, and gave a very nice framework for recurrent neural network. Anyway, but this unfolding over time is a more modern treatment of recurrent neural networks that allows us to use the machinery of feed-forward neural network. So, so I had illustrated this with part-of-speech tagging, where purchased videocon machine gave rise to the part-of-speech sequence of VBD, past tense verb, NNP, proper noun, and NN, a noun. So here at every step, the neural network takes the input word possibly in the form of word vector, and then produces the part of speech. Now the part of speech also comes out as a probability vector. VBD will be the winner probability. Okay, and all the probability values will sum to 1. So if there are, if you make use of pen pause tag set, then there are about 40 pause tags, and you have to have 40 neurons in the output layer. So for the first word purchased, VBD, the neuron corresponding to VBD, will be um, will have highest probability, other neurons having lower probability. In the next word, NNP will win. In the next word, NN will win. Everywhere the same weight will be applicable. Okay, W, V, and U. See how the neural network gets additional input in the form of previous state. Okay, in the current states computation. We'll illustrate this with an example. The other kind of operation is when the input is first processed completely. You get an encoding of the input and then produce an output. The output can be in the form of one classification decision that this statement has positive sentiment or negative sentiment. Now, this kind of holding up the output until the end of the sentence requires remembering long distance dependencies, which is when the annotation vector and context vectors are used, producing what is called the attention framework. Okay, so attention framework, many of you might have heard of, might have used also, but this is mainly to remember some useful information over the whole sequence. So coming back to the RNN model, let me illustrate this with an example. So suppose I have this very simple neural network, a single neuron called H, which receives the input X, and that is a bit 1 or 0. And the weight is U from input to the neuron of value 1. The neuron feeds itself back with a weight value of 1. It produces output and sends it to an output neuron called O, whose input-output relation is simply y equal to x. Whatever input it receives, it produces the same input as output. And the neuron itself has, the H neuron itself has nonlinearity in the form of sigmoid, 1 by 1 plus e to the power minus x. Now this is the sequence which is being processed by this neural network. And here neural network is a single neuron H, compute neuron. The output neuron is a linear neuron and X is the input. The input sequence is 1 0 0 0 1 0. So can somebody verify you're looking at 1 0 0 0 1 0 sequence?
Yes, sir.
Yes, okay. Sir. Yeah. So now first the input is 1, which is made bold. Now 1 gets into the neuron, 1 by 1 plus e to the power minus 1. So that that comes out to be 0.73. 0.73 into the weight 1 is 0.73 goes into the output neuron, which is y equal to x. And the same output is replicated. So this is 0.73. So after seeing 1, the neural network outputs 0.73. In the next step, I receive the input 0. The neural network receives input 0. This is 0, and it also has an input 0.73, okay, which is through the feedback connection. That 0.73 is multiplied by W, whose value is 1. 0.73 plus 1 by 1 plus e to the power minus 0.73 will give rise to 0.67. So on 0, the output from the neural network is 0.67. In the next stage, 0.67 is fed back. Input is 0. 1 by 1 plus e to the power minus 0.67 gives rise to 0.66. Next stage, 0.66 fed back plus 0. 1 by 1 plus e to the power minus 0.66 is 0.65. Next stage, the input is 1, 0.65 fed back. Output is 0.83. Finally, input 0, 0.83 fed back, 0.69 comes out as the output. And therefore, the output sequence will be 0.73, 0.67, 0.66, 0.65, 0.83, 0.69. So now if you put your threshold as 0.6, that anything beyond 0.6 I look upon as 1, then the output sequence will be all ones. If you make your threshold as 0.9, that means anything above 0.9 will be looked upon as 1. And anything below 0.5 will be looked upon as 0. Then all these will be undefined regions. Okay, regions of undefined operation. You'll have to continue the uh, training. Okay, not training. You will have to have a different machine. So this is a machine which is being deployed on this sequence 100010, and the threshold of 0.5 as low watermark and 0.9 as high watermark will make these values as points of undefined decision. So you can see that these values are actually fractions, and it is our threshold which allows us to look upon them as 1 or 0. So I hope the operation of the recurrent neural network is clear by means of this very simple example. Again, you do not see such examples in books and papers, but they are good for understanding the computation. Note particularly the value 0.83, which is coming at the final token of the sequence. This 0.83 is fed back, okay, fed back from the activation of the neural network. Let's proceed further. This was an extremely simple network. Namely a,
Sir,
yeah.
yeah. So in this we can set the threshold according to ourselves, right? Means 0.7 would work, right?
Yes, yes, yeah.
Uh, so it's yeah, means and then we will get a proper prediction.
Then we'll get a proper prediction. Yeah, it depends on the problem, on and your decision to set the thresholds appropriately.
Okay, okay, sir. Yeah.
Now we take a little more complex network, namely the Xor network. Okay, I have an Xor train network, feed-forward network. I would like to operate this as a recurrent network. And this network traverses over a bit string, but looks at two adjacent bits at the same time. So this is the picture. Okay, I hope the picture has come out properly. So input 1 and input 2. So from input 1 I have these, or let me concentrate on hidden neuron 1 and hidden neuron 2. In hidden neuron 1, the weight values are 1 1, reaching 1 1. Threshold is 0.5. So you can see it computes OR, x1 plus x2. The other network is receiving, other neuron is receiving inputs over two connections whose values are -1 -1 each. The threshold is -1.5. So this neuron computes NAND. And the outermost neuron has threshold 1.5. Two weight values are 1, 1 each. This neuron computes AND. So it is AND of OR and NAND, which computes XOR. Okay, so I have this pre-trained network or pre-constructed network where AND is computed at the outermost neuron and NAND and OR at the hidden layer neurons. This is my XOR network. I make it recurrent in the following way. I have a feedback connection from every neuron to itself. Okay, and then I allow I present input vector input sequence of ones and zeros to the XOR network, asking the network to look at two adjacent inputs at the same time. So initially it has input 1 and input 2. Nothing is coming from the state, so assume to be 0. Okay, all compute neurons, output and hidden layer neurons are receiving 0 from previous state. And the input happens to be 0 and 1. So, so the output, what is this 0, 0? One sec. I think these are inputs to it. Let's see. For 0, 0, the output is 0. For 0, 1, the output is 1. Just one sec, okay. Output is 1. I believe there is a bit of problem with the output values. Now let me see once again. Achha. So first I receive 0, 0. Output is 0. This is okay. And these zeros are actually what is reaching over the connection into the hidden layer. Okay, the next input is 0, 1. And here the output should have been 1. Okay, and then this should have got output 1. Okay, all the connection weights are 1. Okay, and then again I have a 1, 1. Because there is an additional 1, the output is 1. Okay, so it is XOR to start with, but I think I should check all the values once again. But I guess you understand the operation. The operation is that each neuron's activation comes back to it through a weight value. Those weight values are also, of course, trained on the data. Okay, trained on the data. And for now, we have assumed that all these weight values are 1. So, okay, let me see what happens to when 0, 0 is input. When 0, 0 is input, then this should compute OR, so output will be 0. This should compute NAND, so output should be 1, which is fine. And I think these are these are actually the outputs coming from the neurons. And now 1 and 0 produces output as 0 because this is the AND neuron. Now next input is 0, 1. So 0, 1 should produce I don't understand this -1 though. Okay. Now I think I should check all the values again. Okay. So 0, 1, this is an OR neuron. This is an OR. This is a NAND neuron. Okay. And the previous input was previous state's output is 1, and that is fed back into it. Okay, so I think I'll re-examine the values. The point I'm trying to make is that the neuron's activation comes back to it, okay, from the previous state for the next state of computation. That is the most important point. Okay, so so these values I'll
Sir,
do double. Yeah.
in this, just wanted to confirm. So the operation at each node is exactly like suppose if we look at the first block of OR, it will be OR of the two inputs and
Mm.
then plus the feedback and then we'll put the threshold, right?
And then it will be compared with the threshold.
Yeah. Okay.
Yeah, yeah. So these are actually perceptrons. Sigmoid neurons will have something else coming out. Hmm. Yeah. So I should recheck the values. Okay. Um, okay. Now we come to a kind of network which has been made famous by Hinton's uh, lecture on recurrent neural network. So here we have seen this neural network before. There are these three neurons, and the three neurons have the connection which is shown here through the feedback and feed forward connection. So the first neuron, second neuron, third neuron is first put down at time step 0. At time step 1, the same three neurons will be replicated. Time step 2, time step 3, same three neurons will be replicated. Now the connection is preserved with respect to the feedback and feed forward connections. So we see that neuron number B, let's call them A, B, and C. B feeds into A by W1 and B feeds into C by W4. So from B, W1 and W4, two feed forward connections are going. From A, there is a connection W2 to B. And from C, there is a connection W3 to B. So same thing is repeated and you have a stack of neurons replicated with connections. Okay, a stack of neurons replicated with connections. So this is a neural network which is unfolded over time. Okay, and we'll see how the training happens. Now there is a bit reversal problem which is also very interesting for RNN. So you see the problem definition is reverse the bit if the current input and the previous output are same. Reverse the bit if the current input and the previous output are same. So initially when you look at 1, you assume that the previous output is 0, you know, vacuously. Now 1 produces 1. Okay. The next one produces 0 because the previous output is 1 and the current input is 1. So 1 and 1, 0. Current output 0, current input 0, current output 0. So that will reverse the bit. You will get 1. 1 is output, input is 0. They are different. So the same input is transferred. It becomes the same output is same as input. So 0. 0 output, current input 1, different. So input gets replicated as output 1. 1 output, 0 input, different. So input replicated as output 0. 0 output, 0 input, 0 should be reversed 1. 1, 0, 0, 0, 1, 1, 1, 1, 0. So this is called the bit reversal problem, but not ordinary bit reversal. It is context sensitive. So depending on what the previous output was, the bit is reversed or not. So this, let the sequence length be 10 and the dimension of each element of input sequence is 1 bit. Dimension of each element of output sequence is also 1 bit. So such a network is shown here. It is unfolded over time. And previously one of the uh, uh, students who was involved in the course did a Keras implementation. So that code you can look at later. Okay, so now how do I train the network when we have this unfolded RNN and it is behaving like a feed-forward network? So there we have to make use of what is called BPTT algorithm, back propagation through time. The forward pass is at each time, backward pass computes the error derivative, And after the backward pass, we add together the derivatives at all the different times for each weight. So let me explain what I mean by this. I take this network, and after time step 3, I know what should be the expected output. Okay, so I am the input available, I have the expected output, and I have these weights whose values need to be determined. How do I do it? Okay, so consider the training scenario. The network is going through different time steps, and after time step 3, I know what the output should be. Okay, so now this has been unfolded over time, and now if this was an ordinary feed-forward network, I would have directly computed the change in weight values after initialization. What is the change in weight? It is learning rate into delta into O. Learning rate is eta, delta is in the destination neuron, and O is in the source neuron. So this is the weight change rule by which I would have got these weight values from the input and output patterns. But the problem is this is a recurrent neural network, and it is actually the same network replicated over time, unfolded. And the stacks are actually the same network repeating itself. What is the constraint? The constraint here is that if I call this ABC and give them suffix 0, at time 0, it is A0, B0, C0. Time T1, A1, B1, C1, A2, B2, C2, A3, B3, C3. So the same neurons, so lower suffix indicates the time step. Now mark the main difference between BP and BPTT, backpropagation through time. Main difference. It is the same network replicated over time or unfolded. So that means if I take B, all the weights from B to A should actually be same. Okay, they are not different over time. All be same because it is the same weight. Okay, the same network is going over the sequence again and again. So the weight B0 A1, B1 A2, B2 A3, all these weights actually are same. So the same thing applies to other weights also. Let us concentrate on B2A weights only. So when I compute the error derivatives or the change in weight values, then when I change the weights, what I'll do is that I will accumulate all the changes in the weight, add them together, and post these weights on all these three weights together. Okay, so the initialization will be such that all these weights will be same. Okay, the initialization, look upon this as a feed forward network, but there is a special constraint now. In this feed forward network, the weights B to A at every layer should be same. This is an initialization requirement. And then when the weight change expressions are found for each layer, they are all added together, and all of them are added to these three weights. And if they started with same initial value, since the addition of increments are added to them, they will continue to remain same. So if the initial values are 1, okay, for each of these weights, B0, A1, B1, A2, B2, A3. These three weights are all starting with 1. Now suppose the change in weight here is 0.5, change in weight here is 0.7, change in weight here is 0.6. Then I'll add 0.5, 0.6, 0.7 and add these 0.6, 0.5, 0.7, which is 1.8 to all of them. Now all of them will become 2.8, 2.8, 2.8. Okay, so this strategy will be used for all the corresponding weights across layers. This is called BPTT, back propagation through time. Any question? There is a slight difference with BPTT.
So here also we'll need a chain rule, right?
What chain rule?
To compute the gradient. So it will also, I mean, lead to exponential situation and
Yeah, yeah, of course. Of course. So if RNN works on a very long string, very long sequence, then your RNN will get into exponential or vanishing or exploding gradient
vanish.
problem.
Okay, okay.
Yeah. So just note this. I will run one input-output pattern on this, get the error values, backpropagate deltas, get the change in weight for each weight, and while changing the weights, we'll just make sure that corresponding weights layer to layer remain same.
Sir, how are
Yeah.
we ensuring that it will get conversed? Because we are not updating the right value. We are updating the addition of all values.
So what is the guarantee for convergence? That's what you're asking?
Yes, sir.
Mhm. Convergence means, in this case, of course, it means that it should bring the error value below a particular level.
Yes, sir.
Okay. Ultimately, we are interested in the lower error value to be something below a threshold. So for that, you have to believe the feed-forward network property. Feed-forward network says that if the neural network is sufficiently rich in terms of its organization, if there are sufficient number of neurons in the hidden layer, okay, then uh, then the network will converge. I mean, so you see, there is no theoretical proof for this. It all depends on whether the network is sufficiently resourceful or not. So consider this as a feed-forward network. Let us not worry about RNN. Does this network load? Load is the technical term, which means can it train on the given data? So I can, if I do not get satisfaction with one layer, then possibly I'll introduce another layer or increase the number of neurons. So these 3 neurons will become 4 neurons, let's say, and then over time it will unfold. So so there is no such theoretical guarantee. We just hope that with sufficient number of neurons this can be achieved.
Okay, sir. And one more doubt, sir. Like in this RNN, do we have this symmetry problem?
Ah, so it's good that you raised this question. I was expecting. Now you see the symmetry problem comes for weights emanating from a particular neuron. So from this neuron, look upon this as a feed-forward network. So when we are ensuring that these weight values remain same across layers, symmetry problem doesn't arise across layers. It arises for connections coming out from a single neuron. So if these two weights, okay, from B to A and C, if they are equal, then I'll be worried, not across layers.
Yes, sir. Yeah.
Okay, so now we move on to okay, look at the notes for some interesting problems. Let me also quickly introduce uh, another very important neural network paradigm called convolutional neural network (CNN). Now, CNN's motivation was computer vision and image processing. RNN was mainly for sequence processing, and language happens to be a sequence processing task. Now, CNN is a combination of feed-forward network and recurrent network if you look at it from a from an appropriate perspective. So let me first give you a very nice development in 1980s. This was called neocognitron due to a Japanese AI researcher, Fukushima. So neocognitron was a very important development, and it was mainly for computer vision image processing and pattern, more I would say for pattern recognition. So suppose my task is to recognize an octagon. Okay, octagon is a polygon with 8 sides, and the octagon consists of 2 vertical lines, 2 horizontal lines, 2 forward inclined lines, and 2 reverse inclined lines. Okay, this is the octagon. So neocognitron proposed that pattern recognition happens in stages. So the first layer of neural networks, first layer of neurons will first recognize the primitives. The primitives are forward incline, horizontal line, vertical line, reversing line. The next layer of neurons will recognize combinations. Okay, so vertical, forward incline, horizontal, first neural block. Second neural block in stage 2 will do the recognition of horizontal, reverse incline, vertical. The third one will do horizontal, forward incline, vertical. And the fourth one, vertical, reverse incline, horizontal. Stage 3 will combine these further and obtain half of the octagon. Half vertical, forward incline, horizontal, reverse incline, half vertical. The first block in stage 3, second block is recognizing the mirror of this pattern. And at stage 4, the recognition of the complete octagon is done. The recognition is complete there. So I have a neural network which, given a shape, will decide if the shape is an octagon or not. So see how compositionality is applied for this problem. The octagon problem is first reduced to its elements, then combination of elements, then combination of elements, and finally the whole pattern. Now the thing to note is this was done back in 1980s, so long back. Okay, and a similar idea is seen in convolutional neural network. So the theory of neural network made tremendous advancement in 80s, 90s, but was kind of languishing. It was languishing for lack of data and computing power. Now that data is available in plenty, at least in some problems, and the compute power has increased many folds, many of these problems are becoming doable. But these people who created these architectures can be looked upon as big visionaries. So we see a replication of these in the following network. Uh, this is very common in discussion on convolutional neural networks. You typically start with an image. So the image is some m pixels by n pixels. Then you set up what is called a kernel on the image matrix. I'll give details later. And each kernel sends a set of weights to a neuron in the next layer. Okay, so the kernel moves over the image column by column. After hitting the right wall, it comes back, shifted by one row below, and again moves towards column by column, shifting by one column to the right wall. Again comes left, and this goes on. So this gives rise to a smaller matrix compared to the previous image matrix. The image matrix gives rise to a neuron matrix whose dimension is much smaller. This stage can be replicated a number of times, and then you do what is called pooling. So you again set up a kernel of a much smaller size and take the maximum value within that smaller matrix, or minimum value or average value. This is called max pooling or average pooling or mean pooling. This is equivalent to feature extraction from the image. Once all the features have been extracted, a feature vector is constructed and that is sent to a fully connected feed-forward network with which we are very familiar. And finally, at the outermost layer, you have decisions on what objects are there in this image. We can see there is a boat. So the boat neuron or the boat block, okay, has this activity of 0.94, the probability value of 0.94, which is high, showing that there indeed is a boat in this image. Dog, no. Cat, no. Bird, no. Okay, so this is the convolutional neural network. The key point here is this convolved matrix of neurons and then pooling. Now this is for image. This is applied to language also. Okay, in language we see its use in the following manner. I have a CNN for detecting the sentiment of a sentence. I like this movie very much with exclamation symbol. I take the word vector of I. Word vector is an n-dimensional vector representing a word. For the sake of discussion here, the dimension of the word vector is only 5. So there are 7 words in this sentence, 3 words and an exclamation symbol. So there are 7 tokens in this sentence. So this is a 7 by 5 matrix. And I want to know what is the sentiment expressed in this sentence. I apply CNN. And I take a 3 rows by 5 columns kernel, sliding over it. And that is equivalent to breaking the sentence into its n-grams. I like this movie, very much, exclamation. So I'm dealing with this sentence trigram by trigram and extracting the features out of these trigrams. Those features are difficult to give meaning to. Okay, it is not as if I'm first doing morphology analysis, then doing part of speech tagging, then syntax tree, then semantic role and pragmatics, and finally the decision comes out. No, it is a 3 by 7 matrix, and from those matrix by max pooling, average pooling, etc., I get some values. These values are feature representations for trigrams. Whether they represent morphology, part of speech, etc., is not really known. This is opaque to me. This is inscrutable. There is, of course, research on can such sliding windows be made to do morphology, part of speech, etc. Okay, RNN has made more progress towards that, but CNN, since it is naturally born for assisting computer vision, would require more work in terms of part of speech tagging, morphology, etc. Because in image, you really do not have part of speech tagging, syntax tree, etc. Okay, so this is a paper by Danny Britz, which is CNN for sentiment analysis. We had done some work in 2017 due to Abhijit Mishra, Kuntal De. Abhijit was my PhD student, and Kuntal De was from IBM at that time. So here sentiment analysis was done both textual features and gaze features. This is the multimodality really. So what we did was we extracted the eye tracking features of the annotators who looked at the data and gave their decision. So while they labeled the data for positive and negative sentiment, we also collected their eye tracking behavior. And each eye tracking behavior was broken up into primitives of fixation, regression, progression, saccade. Those are technical terms, you need not worry, but they are primitives. And they also could be converted into vectors. Then I pass a filter over the textual part of the input and over the gaze behavior part of the input, pass through different filters, collect the features, concatenate gaze features and text features, send to a feed-forward network, and the decision comes out in the form of activations of two neurons. One neuron saying whether it is a positive or negative sentiment, and the other neuron saying is it sarcastic or not. You might ask, how can sarcastic sentences be positive sentiment? Not normally. Sarcasm typically is associated with negative sentiment. Positive sarcasm arises in case of fun. Okay, suppose A wants to make fun of B, but in a harmless way. A can be sarcastic of B without meaning to injure B, and that would be positive sarcasm, mainly in the sense of innocent humor. But sarcasm typically is meant to hurt or injure the sentiment, and that's why sarcasm has more closer association with negative sentiment. So coming back to the technique, here is a neural network with two compartments, one for eye behavior, the other for the text. And the features are collected from both compartments, concatenated, sent to a feed-forward network, and out comes the decision. Now a little bit of detail on what happens in convolution. This is a very popular example. You can see it on medium.com and also research papers. So the kernel is 3 by 3. How is the kernel to be decided? Depends on the problem. Those of you who have made use of support vector machine, gone through the theory of support vector machine, know that kernel design is non-trivial. Just like designing the hidden layer of a neural network, it is non-trivial. It depends on the problem, and it gains from the experience of the problem solver. So in this case, I have a 3 by 3 matrix as the kernel, where the values are 1, 0, 1, 0, 1, 0, and 1, 0, 1. Why 1, 0, 1? Depends on the problem. Now I bring this kernel and place it on top of this image, which consists of black and white pixels, black for 0, white for 1. And I place it on the first 3 rows and first 3 columns, multiply it by these kernel weights, and I get the value 4. You can verify that 1 into 1 is 1, 0 into 1 is 0, 1 into 1 is 1, 0 into 0 is 0, 1 into 1 is 1, 0 into 1 is 0, 2 zeros will again give 0, 1 into 1 is 1. Once, therefore plus 4. Now I shift it by 1 column. Now I have 1, 1, 0, 1, 1, 1 and 0, 1, 1 interacting with the kernel. That will produce a value of 3. Shifted by one more column, I hit the right wall, I get 4. Now I come back to the left wall, but shifted below by 1 row. Here I get 2, then 4, then 3, then 2, 3, 4. So I get a matrix of neurons with values 4, 3, 4. Now in this case, of course, I'm just adding the activations and putting it on the neuron, but the neuron itself is typically a nonlinear element. Okay, a ReLU or a tan H function, because that ensures better convergence of the network. So this 4, 3, 4, 2, 4, 3, 2, 3, 4 matrix of neurons can be further reduced, but may not be necessary. But at this point of time, I can take a 2 by 2 kernel. Now I'll call it a filter. So that 2 by 2 filter will simply take the average of values, okay, or take the maximum of the values. So that will be the details of the convolution operation and the filtering operation. There is a bit of ad hocism here, I agree, that why averaging is giving me the feature, why is max giving me the feature, those questions are unanswered really. But CNN has been quite widely used for natural language processing also, though RNN is more common. So with that, I think I'll stop. I gave you some idea of convolutional neural network. There are worked out examples of RNN. All the slides will be made proper and uploaded. Day after tomorrow is your examination. And examination will be multiple choice question type. I have sent a WhatsApp message which will be on Teams and Moodle also. If you find that none of the answers is acceptable to you according to your judgment, just write your justification for your answer and that will be giving credit. Some input from you is required. Okay, so today's summary is that we did RNN and CNN, at least an introduction of this, uh, to be elaborated much further in the next offering of deep NLP course. Okay, you can ask questions.
Sir, so in the book EM for word alignment example, row headers are English words and column headers are French words. But in the notes, column and row headers are interchanged. Is it okay to interchange the row with the columns? If we go with the notes, then column sum should be 1. And if with the book, then row sum should be 1. Which notation should we consider?
Yeah, good point, and I'm sorry about the confusion. First, to decide what is the source language and what is the target language. Okay, decide the source language and the target language. If it is PE given F, that is probability of English given F, where F becomes the source sentence and E becomes the target. F is source language, E is target language. Source language is kept on the row, target language is kept on the column. Okay, that is the form convention which needs to be followed.
Row sum should be 1, right?
No, not row sum. So we are asking, what does Troya correspond to? 3 or rabbits? Okay, yeah, row sum should be equal to 1. Yes.
In the vocabulary mapping slide, why there are repeated words in vocabulary?
Repeated words in the vocabulary? Was it?
Yes, sir. This one. So vocabulary, we consider it as a dictionary, right? So there should not be a
Yeah,
repeated word, right?
yeah,
So
yeah.
okay.
Is there a repetition?
Yes, sir. In BF, like hey, hey, and be, like there are repeated words.
Oh, अच्छा. Should be made unique. Yeah. Right. Then
Varad asks, what was the need of using RNN for XOR? Do the feedback connections speed up training as compared to a simple two-layer neural network?
no. So this Xor network was just taken to show what an assembly of neurons will do. Okay. The idea is not to solve a sequential XOR problem. No. So I'm just trying to tell you that uh, it is easy to explain recurrent neural network with a single neuron. Okay. But what happens if I take multiple neurons and a more complexly built neural network? It has nothing to do with XOR as such.
Saurav asks, can or should we explain the options that we select in case of any ambiguity in endsim?
No. Ambiguity means
I mean, so can we, so if we think that thinking in one way, we are getting option A, like it happened in the last quiz. So like we thought greater than equal to and that thing. So if we explain our thinking and then mark options.
okay. Yeah, you can do that. Yes. So if there are multiple answers possible, then one thinking leads to this answer, another thinking leads to another answer. Can you write it down? Yeah, you can.
Hello, sir.
Yeah.
So in the XOR problem today,
Mm.
so in the final neuron, what was the feedback given? Like, can you just explain that? Like in the
What was the
topmost,
feedback given?
yeah, like which input was given as the feedback to the final neuron in the topmost layer in the XOR problem?
Yeah. The final two bits are 1 and 1.
Yeah.
And if in the previous state, if the output from the outermost neuron was 1, this is being fed back.
Okay.
Okay? And same thing applies to all neurons in the network. Whatever was their output previously is fed back.
Okay. Thank
So basically in this, should the number of input samples should be only 4 because we have two square possible combinations, or we can feed it as many times as we want because the feedback is always different in every time.
No, no. What is in sequence? Okay. And
Yes.
the Xor network slides over it, shifting one token at a time.
Oh, okay, okay. So that can be as long as we want, right?
Yeah. That's where that was the attraction of RNN. Otherwise, CNN had to pad a lot of things if the input was smaller.
Okay. Also, sir, could you put the, you said there was some mistake in these slides. Could you please
Yeah,
put the correct slides?
correct, correct all of them. Yeah, surely.
Okay, thank you, sir.
Yeah. Oh, that's all, Riptesh.
That's all, sir. Yes.
Yeah. Okay, so finally, let me say that I really enjoyed teaching this course. And you were all great students. Nice meeting all of you. And hopefully we'll be in touch also continuously in future. One final message I'd like to give is that for doing good work in NLP and to appreciate NLP, you also have to give equal importance to language and the language phenomenon and what happens in the brain, what is cognition, where does language arise, how does language change. Okay, this is a very big world of cognitive science, linguistics, philosophy, even physics and mathematics, of course, statistics, of course. So that's it. There is this very big world of many things which have come down to NLP over centuries. So it is not only technique that forms NLP, not only computation, not only RN and CNN that forms NLP. This whole world of language also is very important. And to be able to do good work, deep work, you will have to appreciate language phenomena also. And appreciating language phenomena means you have to appreciate languages also. You have to appreciate what is going on in Konkani, what is going on in Assamese, what is going on in Hungarian, what is the property of Turkish as a language. Those things are also very intriguing. Why does human mind create those constructs? Why is it that French decided to put adjective after noun? English puts adjective. अच्छा लड़का है. Why is it that Bengali doesn't have anything of high? Ram bhalo chele. It stops there. Ram अच्छा लड़का stops. No hai. Then all these language phenomena are very intriguing, very interesting, and talks and says something about the way human mind operates, which is very rich. Okay, so do give equal importance to language and computation, then only you'll be able to enjoy NLP and will be able to do good work. All right, so we'll be in touch and thank you very much.